Girish, can you? All right. So good afternoon, welcome back. So we are now in lecture 4. So we'll be slowly transitioning from data science to probability and statistics, and then we'll get on to introduction to machine learning. Then we'll come to some algorithms in machine learning and Bayesian and so on. And then we'll see some further techniques in machine learning and end the course with some applications where we have done some live wire problem using machine learning and all the principles which we will have seen in the 11 classes or so in the last 12th or 13th lecture. All right. So next week, I would like to go from 4:30 to 6, because I might miss the class on first. Okay, I'll be here, but there is some other afternoon. I don't know. I may get stuck in some traffic in Bangalore because I have to go out. So 4:30 to 6 next week, and then I will again go from 4:30 to 6 on the class on 8th. First, we will not have the class. Going up to 6, any problem for anybody? Should be fine. I'll give a break of 5 to 10 minutes, whatever in between. Is that okay? So that we can take 2 extra half an hours and make up for 1 class. Is that all right? Or we can start at 4:15 and go up to 5:45. 4:15, is there any objection if we start next week? Next week alone. Anybody has any problem? Anybody has a class up to 4? Hello? Is it okay if we start at 4:15 next week? Then we'll go from 4:50 to 6 with a 5 or 10 minute break and be done with it. That's it. And then, so we would have already compensated 1 class. Okay, so I will let you know by email or Girish will inform you. All right, so please mute yourselves. Hey, who is talking? IIT Madras? Huh? All right, okay.
Okay.
Okay, so let's start with this quote. Information is the oil of the 21st century and analysis is the combustion engine. Okay, so hello.
Okay. So it's not. Hello.
Hey, why am I getting feedback?
Okay, it's not yours.
Hello, Girish? Hello,
Yes, sir.
Girish. Hey, can you just find out whose mic is on and tell them in chat, in the chat box?
Okay, sir. I'll ask them to mute.
Okay, but some crosstalk. Are you talking in the lab?
No, sir.
Okay, all right. Okay, so information is the oil of the 21st century and analysis is the combustion engine. So you require both the engine as well as the oil to run the engine, all right? So there are many tools and techniques a data scientist is expected to know or acquire as new problems keep surfacing, okay, which need to be solved. So often the tools and techniques are often hard. It's quite difficult to distinguish. In this course, we look at a few tools and techniques without worrying about a particular tool or programming language. Though we have already told you that Python is one of the best languages in order to implement data science and ML. So Pratik came on board last week and gave you a hands-on. He just gave a 101 on Python, and we solved this problem of child mortality. We did some work with the data available from UNICEF. Yeah, please mute yourselves because it's disturbing the whole class. All right. Okay, so now we'll first look at the basic differences. What is data analysis? What is data analytics? Analytics is a term often new to the scientific and engineering community. So we'll flesh out the terminology and then we'll get on to some statistics. So slowly I will inject mathematics and statistics into this. I will keep it at a level which is bearable, but some mathematics is unavoidable. Otherwise the whole course will become like a blah blah. All right. So what is unavoidable here is a review of basic. Please mute your mics, since if you're not speaking, there is no need for the mic to be on. Okay. What is unavoidable here is a review of basic statistics. You should not get rattled by this, because if you want to progress anywhere, either in data science or machine learning, using machine learning for data science or your scientific pursuits, you should be strong in statistics, regression, statistics, analysis, all these tools, you have to be very strong. Otherwise, we cannot make much progress. All right. So some people often say that data science is considered as a fancy term for statistics, but we already saw that it is not really so, because we have to really, the basic difference is we handle large volumes of data in data science. And so therefore, the progress in data science is synonymous with progress in computers, hardware and software, memory, and so on. Girish, can you just, Girish, can you help me?
So one person, Vivek,
You just say, Vivek, please mute your.
I directly messaged him, but he did not respond.
How do we mute him? Can I mute?
Yeah, you can mute everyone actually.
How do you do that? Participants.
Yes.
Yeah, then go to participants. I think it is okay now. Let's get on with the class.
Yeah, no, it's okay.
Okay, so this should not rattle us, as often data science is considered as a fancy term for statistics, but this yes and no. Okay, we already saw that. So what is the difference between data analysis and data analytics? These two terms are often used interchangeably, and so this could be quite confusing. So, but however, we'll try to flesh out the differences between the two. There are a few key differences between the two, though. Okay, so I'm just taking it from this book by Shah, and that's what I'm using now, a hands-on introduction to data science. So according to Kasik from Boeing, watch this very carefully. In my terminology, data analysis refers to hands-on exploration and evaluation. So data analysis refers to hands-on exploration of the data and evaluation of the data. Data analytics is a much more broader term and includes data analysis as a necessary component. Fine. So whatever has been given in italics and in that orange color, we just said that data analysis is a part of data analytics. But the last 3 lines of the definition actually tell you how data analytics is the superset and data analysis is the subset of data analytics. Analytics defines the science behind the analysis. The science term means understanding the cognitive processes an analyst uses to understand problems and explore data in meaningful ways. So if you feel that it's all semantics and just they're playing with words, basically, if you do mechanistic analysis, report like mean, standard deviation, kurtosis, this thing, interquartile, this thing, blah, 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 all that, that is data analysis. From that, you see the underlying meaning in data and try to forecast, try to predict the behavior. That is analytics. Using data analysis to keep predicting or forecasting. That prediction and forecasting is usually not considered as a part of analysis. Analysis is to dive deep and understand. You stop with understanding. But if you want to solve the problems of the world, stopping with understanding doesn't take you in, doesn't help much. It helps to a certain extent, but you're not able to go to the end of the problem. Therefore, data analysis precedes data analytics, and data analytics is a all-encompassing, an umbrella-like terminology, where using data analysis, you actually go on to do some prediction or forecasting. Okay. One way to understand the difference between analysis and I already said this, analysis and analytics is to think in terms of the past and the future. Analysis looks backwards. You're always looking at what happened in the past and then providing scientists, marketers, economists with a historical view. You're often obsessed with the historical view of data, historical view of phenomena, whatever. On the contrary, analytics is you make use of the historical data, use your gut feeling, intuition, insight, what have you stuff, and then build some analytic models where you predict the future as a result. So you want to predict the future GDP growth rate, what will happen to the Antarctic ice sheets, what will happen to the rate of mass loss in the Himalayan glacier. Okay, so I mean, what will happen to the forest cover? What will be right? What will happen to how much of the east coast, the Coromandel coast, will get eroded? I mean, these are all not part of data analysis. These are all part of analytics. So analytics uses mathematics, statistics, descriptive analysis, and predictive models to gain knowledge and insights from the data. Analysis uses mathematics, statistics, descriptive analysis, and stops. Analytics uses mathematics, statistics, descriptive analysis with a view to develop predictive models. That is why you need to know what is a clustering algorithm. what is a clustering algorithm, how to fill a data. Okay, so how to classify data. So classification is a big problem. Often there is a 0 and 1. I told you the example in the first class. I want to cross the road. It is not basically about 6.425 because scientists, we are obsessed either with our Casio calculator or a computer. We want numbers. There it is digital. I will either cross the road or I will not cross the road. You tell me. The model should tell me. If I cross the road, it is 1. If I don't cross the road, it's 0. So the output of the model is either 0 and 1. But input can be a lot of variables. It could be whether I'm healthy that day, whether I'm carrying this thing or whatever, what have you stuff, and whether there is auto rickshaw coming. So there are so many other variables, but output is binary. It is digital. It is 0 and 1. Therefore, we need to learn these algorithms to move forward. We can't always take x1, x2, x3, x4, fit a nice correlation and predict y. That's what scientists and engineers have been doing. So we better borrow these bright ideas from computer science and implement it so that we can solve. So once you're strong in your domain, use these tools. So data science, machine learning is a tool. It's just a tool. If you're strong in science and engineering, you should be able to learn this tool. If you learn this tool, it is going to certainly help you. You can solve problems. You can go to analytics. You'll be able to predict. Okay. Eventually, we can make a mark. All right. In whichever field we are working in. These insights from data are used to recommend actions or guide decision making in a business contract or even in policy decisions of governments or organizations. For example, the Intergovernmental Panel on Climate Change, IPCC reports. Now, I think the 6th report has also come. So the reports on future climate risks, what are the measures you take for mitigation and adaptation? So they are based on not only it's just not past data, right? They run the RCP scenarios, the representative concentration pathways. You look at various scenarios of carbon emissions and see how it will impact the global temperature, the air quality, whatever. So the series of host of parameters. So these predictions are based on, these are all based. Finally, they are saying that there is a report. First, the first part of the report is a report for policy makers or something. That will be like 40 or 50 page document, right? It is freely downloadable on the internet. Take a look at it. I just took a look at it day before yesterday. So it is based on past data plus models plus insights plus future projections. So past data plus models plus insights plus future projection. Past data plus models plus insights alone will get you papers, you'll get citation, impact factor, science paper, nature, whatever. But you'll have to do the future projection. Only with this, you'll be policy. So we'll be able to advise policymakers, whether they take it or not, we'll give the advice. So they'll be able to take decisions. All right. So we get past the analysis stage. We cannot stop with analysis. All right. Classification of analysis, data analysis techniques or data analytic techniques. So you can say, since you use some analysis and analytics, so I think I use it interchangeably here. Let's get on with this. Descriptive analysis of statistics, diagnostic analytics, predictive analytics, prescriptive analytics, exploratory analysis, mechanistic analysis. All these things seem to be daunting, but we will just dissect them and then we will see one by one. 1, descriptive analysis, 2, diagnostic analysis, and 6, mechanistic analysis involve heavy use of statistical concepts. So in all the ensuing lectures, we look at whatever is given in orange color. But in today's class, next half hour, we'll try to do 3, 4, 5, predictive, prescriptive, and exploratory analysis. Okay, just see the basic principles underlying this. So predictive analytics. Now let us take a quick look at the other 3 types of analysis techniques. Analytics technique, whatever, namely predictive, prescriptive, and exploratory analytics. Predictive analytics. What is this? This has roots in our ability to predict what might happen. These analytics are about understanding the future. You want to understand the future by using the data and the trends we have seen in the past, as well as emerging new contexts and processes. If you say that I'll use the past data and trends, everything cannot be in extrapolation, okay? Because non-linearly changes are taking place. Therefore, we should be smart enough to not just do only a trend analysis of the past data, but in the context of in the context of new scenarios, new situations, and new socio-economic engineering processes and scientific processes and products and these things and which are taking place because of the rapid changes taking place in society, we should be able to model them and put it into this model so that we give some meaningful projections for the future. This could be at short term, 2030 to 2050, mid-range 2050 to 2070, or then 2071 to 2099 or whatever. So you can put 20 bunch it into, bin it into 3 short, medium, long term, each of 20 years, 2 decades. whatever, 25 years, whatever, right? So even the child mortality rate, rate data set can be used for future projections. But instead of just looking blindly only at the data, can you see what are the various infections that are taking place in the world? So can you divide this data further into the mortality rate in Africa, this thing, Asia, Europe, and this thing? Can you link it up to the GDP growth rate? Can you link it up to the women's literacy rate, the average fertility rate, the average age at which they start bearing a child? So if you look at, you dive deep, dig. So you're now just not a statistician, okay? Now you're getting into sociology. So you're getting into sociology, public health, and all that, and use all your domain knowledge plus statistics. And then you give, if you want, you can take even a survey, whatever, with doctors and all the social workers and all that. Then do all this. This may be a good topic for a public health. Somebody who is doing a PhD in public health, probably. Okay. So therefore, even the child mortality rate data set, which we were in the last class, can be used for future projections. Okay. So predictive analytics is usually done in the following steps. First, collect the data and clean it up. What is data cleaning? We all know about it now. Insert or ignore missing data using scientific principles, in a quote unquote, okay, within quote, scientific. Cleaned up data can help us in obtaining hindsight in relationship between the typo of the relationship between different variables. A scatter plot between the X and Y, the dependent and the independent and the dependent variable, is a good place to look for hindsights. Okay, the next stage in predictive analysis is to confirm the existence of such relationships. This is where regression tools will help. We will do regression in the next class. From the regression equation, we obtain insight from hindsight. Hindsight is based on past. So from hindsight, you obtain insight. Insight is you try to get some fundas or fundas. Finally, based on the identified patterns or insights, we can predict the future. That is foresight. So from hindsight, you get on to insight. From insight, you get on to foresight. This foresight is never a part of normal statistics and probability course. Everything stops with insight. You may not even do insight, hindsight, and if you just report all the numbers, average height of the student in the class is this, blah, 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 all that. Now, if you do some fundas, the average height is increasing because the growth rate is increasing, because the health of the people is increasing. The average height is also increasing because the life expectancy of the world is going up, whatever. So if you're able to build a model, so can you build a data-driven model with this instead of just always going to Newtonian, this thing that force is equal to mass into acceleration? Okay, so, right? So you start with m into d square, v by dt square, all that, put the two boundary conditions at t equal to 0, t equal to something, x equal to something, velocity something. We have been doing this for 300 years. Is there some other way of doing it? Is this the only way of doing science? That's what the data science people are telling us. So don't try to use always a differential equation or integral equation for this. So you can do it, all this. You can also get insights from the hindsight. That hindsight will come from the data. So if the humongous amount of data, this data can drive some models. That is the basis. Finally, based on the identified patterns or insights, we can predict the future. Foresight. The above steps can be pictorially and succinctly represented as follows, but this is just an improvised version of what is there in Shah's book. Okay, you can see a lot of data. It's all cluttered up. Left side, collect data. Then now you sort it out. You clean the data. If there is something which is not good, you remove that. Then you identify the patterns. So now it's all jumbled up on the left side. Now as you move to the right side, you start arranging. The first is a set of squares, the first column. The second is a set of whatever, rhombus, I think. The third is a set of circles, okay? Then you put some 3 other patterns, then some patterns are missing. And then now you make the predictions and then fill up whatever is not available. That is predictive analysis. So this predictive analysis looked at the left-hand side, hindsight. Then you learn some insight using the second box and the third box. And then with that, you're using all the knowledge at your command and your insight and your intuition to fill up this one. So this is how some randomly organized or disorganized data is put into patterns, and the missing things are also inserted. So this is predictive analysis. This is what business management people, all the computer science people, all these people, machine learning people, all these people are trying to do. For example, if you go to Amazon and keep on buying things, so it will say that based on your past record, next time when you log in, it will tell you based on your past record, this t-shirt is available. Okay, Girish Kumar, you were asking for Nike shoes. Now the Nike shoes is available at 50%. So who is telling all that? It's all machine learning. It's all the data science, machine learning for data science. So some lot of number crunching is going on. It is tracking the behavior of all the people who are logged in. Okay. All right. So predictive analysis is used in several fields. So you want to do, for example, statistical predictions of, say, the track of a tropical cyclone. So you say that, let's say the low pressure is formed and then it becomes deep, and it becomes a deep depression. Then it becomes a cyclonic storm. Then as it approaches the coast, it intensifies into severe cyclonic storm based on IMD-based classification, whatever. Now what you do is, if for the last 24 or 48 hours, a cyclone which originally started as a low pressure in the Andaman and Nicobar, somewhere near Port Blair, is tracking in a particular way. Now use your huge data set from 1847 or what have you stuff from IMD and see if some cyclone has tracked along this for the past so many years, what is its likely track? So this is a pure statistical brute force. It's a brute force data-driven approach. But now we use WRF model, this thing, there are many models, UK Met Office model, many models available. So if you are if you're just a statistician, what you will do is, you will just look at the past data and try to see, try to get a path, okay? Try to get a path in which past cyclones have behaved. But the only tragedy of the whole thing is, you will not be able to get a track which was not seen by the data in the past, okay? So that's where the problem is. But suppose you're able to use this statistical model as what is called a prior knowledge. And then you also have your simulation. You do your fluid dynamics simulation, and also at the same time you're having some guidance from some satellite data or weather buoys or ships. Then you can combine all this. You will be in a much better position. You will be in a much better position to exactly predict the landfall location, plus or minus 50 kilometers, 100 kilometers, whatever stuff, and landfall time, plus or minus 3 hours or 4 hours or whatever. So therefore, this predictive analysis uses statistics, data science, machine learning, modeling, measurements, and everything. Whatever is there in a buffet meal, whatever is there. Okay, so starting from a soup to a dessert, everything is available. So in the form of data, measurements with different errors, with different standard deviations of different quantities available at different spatial and temporal scales. You also have a numerical, you also have a mechanistic model. If you can combine all this, then you're good. Then you're cooking with fire. All right. Determination of risks of patients with pre-existing illness. How do they decide how do you decide based on the age and this thing, your height, weight, and all that BMI, whether you have got diabetes, BP? Based on that, they will increase the insurance, right? If you've seen either you or your uncles or aunts or parents or grandparents taking this, so they will assess, and beyond a certain age, they will not give insurance cover. So this is basically predictive analytics, because they are taking a huge risk. If somebody is covered for 25 lakhs, and imagine 20 days after taking the insurance, his kidney failed, and so there has to be dialysis followed by kidney transplant. It costs 15-20 lakhs for one guy who probably paid a premium of 40,000 or 50,000. Therefore, 20 healthy people or 30 healthy people should take the insurance, so that one or two of them at the most are the unfortunate victims of something like this, of a serious disease, life-threatening disease. Therefore, the calculation of medical insurance premium is a lot of machine learning, lot of data science is used. Now, predicting the GDP of a nation, for example, Indian GDP is strongly related to the ISMR, Indian summer monsoon rainfall. So can you do a predictive analysis and take this as one of the key parameters? And then based on the rainfall, can you tell how the GDP growth rate will be or whatever it will be? If it's a near normal monsoon, what will happen? If it is a deficit monsoon, what will happen? If it's a drought, what will happen? If there's excess rainfall, what happens? All right. Okay. Prescriptive analytics is even more. So it's an area of analytics. So this is up and coming, an area of analytics dedicated to finding the best course of action for a given situation. This is what top management will want. So I want to move into electric vehicles. What segment I will do? Will I do a sedan? Will I do a SUV? Will I use a hatchback? I will do a luxury or this thing, or how will I test the market? What sort of batteries I'll use, and what will be the power rating? What will be the range? What will be the cost? Okay, so because there are not millions of electric vehicles already there. If you wait for others to this thing, then whoever starts first will have an upper hand. Therefore, you have to take the plunge. Otherwise, you don't do business. Okay, if you are in business, you have to take that risk. So, as they say, you'll have to take a calculated risk. So, in taking this calculated risk, the prescriptive analytics will be very helpful. So the process followed in prescriptive analytics is analysis with statistics, followed by finding the connections among various parameters and variables and the relation to each other to address a specific problem, which can often be prediction. So these are all tough. Often, sometimes that's why this can go RE, AWRY. Therefore, this has to be fraught with little bit of, I won't say suspicion. There's a little bit of doubt, so you'll have to tread with caution. All right. Prescriptive analysis can also suggest options for taking advantage of a future opportunity, right? The advantage of future opportunity, for example, green hydrogen or clean hydrogen is coming. I've already invested thousands and thousands of crores in my internal combustion engine. So as the world is moving, a lot of research is going on electric vehicles. Can I make some auto rickshaw based on hydrogen? This hydrogen I produce by biomass gasification, or some Reliance or Indian Oil will do it. So there will be future opportunity. Right now right now, tomorrow itself it won't sell. But suppose I'm saying I'm ready to invest. I'm ready to take the plunge. I don't want any returns for the next 10 years. I'm looking at 2033 or 2035. I will have a car or auto rickshaw which will run on hydrogen energy. Will you take that risk? So you do all these models and see what will be the cost of hydrogen. 1 kg of hydrogen, how much will it be? 100 rupees, 120 rupees, 150 rupees, whatever. Nobody knows now because hydrogen is not there in the market. Okay, only LPG, CNG, whatever. So this, but we cannot wait. So it's all disruptive. Changes are taking place very fast because there are two groups. There's somebody who is working on electrolysis of water to get hydrogen. There are other people who are doing it biomass. Okay, some people say I will ditch hydrogen. I will straight away go with lithium-ion battery. So there are a lot of competing technologies. Therefore, if you are a company or an investor, if you're having money, if you're an angel investor, you want to invest, where will you invest? Okay, all these things are coming under analytics, prescriptive analytics. Okay, and you'll also look at the implications of each. Okay, example, IPCC reports on climate change, mitigation and adaptation strategies for various climate scenarios. Okay, RCP 4.5, RCP 6, RCP 8.5. So these are all giving various emission scenarios. How much is the world committed to reducing the emissions? Okay, the environmental impact assessment of projects. Okay, the future environmental impact assessment of big project which is coming up. Okay, business decisions, healthcare practices, apart from, for example, simple example, apart from height, weight, body mass index, fat percentage calculation, and so on. If you probably include, if the doctor includes diabetes, LDL cholesterol are added as filters, and then the treatment can possibly be more focused. So bring in more parameters with which you'll be able to correlate the health. So this, doctors will say, this is called the disease burden of society. Okay, the disease burden of society. The society has to be healthy. Only then the GDP will grow at a faster rate. Last 2 years have been a disaster. The disease burden of the world has been extremely high. Many people have fallen sick. Okay, and over and above that, there are other illnesses because they are afraid of COVID. They have postponed all their other things. So that is also, for example, cancer patients have not gone for radio or chemo or whatever. Somebody has not gone for surgery, gallbladder surgery, whatever. So it has increased. So it has a compound effect. Okay. So in these decisions, how will you now, if you want to get back the customer, you want to put a discount for some procedures, okay, or a day elective surgery, what business model will you do? Okay. So all these things are basically prescriptive analytics, right? Okay. What is EA? Exploratory analysis. Often when we work with data, we may not have a clear understanding of the problem or the situation. Yet we may be called on to provide some insights. This involves some kind of exploration. You just explore, you just have fun with the data. Okay. Possible approaches include, first you visualize the data, you plot it, creatively plot it, and so on. Okay. Separate the mean, look at the variation, look at the standard deviation, do all kinds of jamela and see whether you're able to see some hidden patterns, and whether you're able to see something which other people cannot see or not able to see. Okay, so EA is rather a philosophy, and nobody can teach you how to do EA. So this is a gut feeling, intuition. It comes from insight, experience. Also, so you have a raw intelligence. You have an intuition. You have to say, yes, I think it's going to work. So that kind of this thing you should have. Okay, so basically you dissect a data set. It is a philosophy of how to dissect a data set, what we look for, how to interpret the outcomes. I'll give you some simple examples from our subject, atmospheric science. There are Hofmuller plots in atmospheric science, Taylor plot, anomaly plots, and so on. Let us look at a few of them now. Okay, now forget about the right side. Take the left side. X versus Y. I give a random 10 values 1, 2, 3, 4, 5, 6, 7, 3.4, 1.91. What is this pattern? Let us look only at the first two columns. Then it says that, okay, you know that as X increases, Y decreases. All right. So it is having a reciprocal relationship. All right. Okay, I will plot it on the right hand side. It looks like it is exponential. I'm not so sure. But what I do is some gut feeling says that I can do some jugaad. So instead of plotting X versus Y, I open up a new column, which is 1 by X. And when I plot 1 by X versus Y, it becomes a straight line. Okay. What is this? The Eureka moment has arrived. So can you do like this? So in all the cases, it may not be so simple, 1 by X versus Y, but that's where you are. That's where you have to put your this thing, right? So that's why a data analyst gets so much salary. So you'll have to figure out what are the ingenious ways of cracking this. Okay, now when we plot Y versus X, it is suggestive of an exponentially decaying whatever. But however, it's not very clear. The moment we plot 1 by X versus Y, we see a linear relationship, and the aha moment arise. I cracked it. So the controlling variable is 1 by X. If you know 1 by X, I can predict Y with using a regression. Okay, that's what it is. All right. So I can do a predictive analytics. So exploratory. So first I do exploratory analysis. With that, I know that I can do the regression, which is a predictive analytics. So EA involves a combination of rigor, creativity, innovation, and the Indian jugaad, okay, or what have you. Some key approaches that will be of help are data clustering. Data clustering means you organize. Okay, now heights of people, correlation. First divided into men and women. Okay, the first thing you divide them into men and women. Then put various features or attributes and dissect the data so that some clusters emerge. Once these clusters are emerge, you will be able to see the underlying patterns more clearly. Okay, visualization, classification, and so on. We'll talk about classification and so on a little later. Visualization we'll see now. Okay, so this is a plot of the reflectivity. What is a radar? So let's say a radar is on board a satellite. So the signals are coming from some signal is sent from the radar from the top of the satellite. Okay, or let us say that it is a upward facing radar which is on the ground. Okay, the Chennai Doppler weather radar, which unfortunately sometimes it doesn't work. So it is sending waves at electromagnetic waves at 13.8 gigahertz. Okay, for example, when there is no rain, the rays will go and nothing will come. So the reflectivity will be 0. So therefore, reflectivity equal to 0 tells you that rain is 0. It's very clear. Now, if you've got a lot of rain and on the top you've got ice particles, okay, you've got big rain particles and so on. If you send waves up, then the waves will be reflected back. So the instrument will collect back. So the stronger the reflectivity, the denser is the hydrometeors. What are the hydrometeors? Precipitating water, okay, precipitating ice, cloud, liquid water, cloud, ice, water we stuff, and gropal, snow, water, which are in other continents. You may also have ice once you cross the bright band, more than 4-5 kilometers, okay, above the mean sea level. Now, this is if you look at the relationship between reflectivity and rainfall, there is a direct relationship. As the reflectivity is more, therefore the rain content, the water and ice content in the atmosphere is more, and therefore using a fluid dynamics principle, you can say that there is a Bringy and Chandrasekhar equation which lets you calculate what will be the expected rainfall rate in millimeters per hour if this is the concentration of the hydrometeors. Therefore, using the radar, so the radar reflectivity can be used as a proxy for the rainfall. Now, if reflectivity is shown in the x-axis, the rainfall is shown in the y-axis. So the ZR relationship is something like this. So you can do a creative plotting. So what is this? Basically, let's look at what is called a scatter plot. A scatter plot depicts a relationship between two variables. A scatter plot is also called a scatterogram. Okay. Also called a parity plot. The scalar values of two variables, one is shown in the abscissa, the other is shown in the ordinate, used to emulate numerical relationship between the variables. For example, the observed reflectivity is related to the rainfall. This is called the famous Marshall-Palmer. Oh, what? Not Marshall-Plumber. Girish. Huh? Yeah. It's called the Marshall-Palmer distribution. Huh? Okay. So that is a famous Marshall-Palmer distribution, Z equal to AR to the power of B, where A and B are constants, which can also be inverted as R equal to C Z the D. So from the radar instrument, if you get the Z and you're able to calibrate the instrument and know the C and D, this could be season wise, month wise, whatever, location wise, whatever. So that is a calibration exercise we have to do. So then you'll ask me, sir, if you have to do calibration, where is the source for the truth? Truth is elusive. Don't talk. Truth is very difficult. What is truth? We don't know. Because even in dreams, you see something. Okay. You see that a tiger is chasing you. Okay. But when you wake up, the tiger is not there. But your experience is real, but the tiger is not there. So truth is very difficult. For practical purposes, in this case, the truth could be some IMUG data or something where all the satellite merged data available from other investigators, or simple ground truth available from radar, rain gauge, or from AWS, automated weather station, and all that. So, okay, suppose you know the rain rate from some other sources, you know the radar reflectivity, you measure the radar reflectivity, you can fix the C and D. All right. So what are we doing now? We are talking about creative plotting. Okay. So now you can change this. You can change this scatter plot. What you can do is you can use this. So I think one plot is missing. Based on the reflectivity and rainfall, you can measure what you can do is rainfall gauge. Then you do rainfall radar. Okay, and if you get like this, it is fine. That means so this is the 45-degree line. So this is called the parity line. Okay, so that means it is doing reasonably when parity plot. So this is called this is the parity line. Okay, now that means you're doing so whenever this gives 30 mm. So you're probably getting some 26 mm, which is all right. You can't get 30 mm, it cannot be like. But if you get a parity plot like this, but here you do like this, okay, then it seems that whenever the rainfall is low, this radar is able to capture well, but whenever the rain is high, the radar seems to be saturating. So either there's a calibration problem or there's a sensor problem or something, the Marshall-Palmer distribution, the C and D have to be reworked. So it is cause for worry and cause for suspicion. There is some higher order effect, which this simple correlation, the Marshall-Palmer is not able to predict. Or we don't know, this could be stratiform rain, this could be convective rain. So I would need to have separate correlations for stratiform rain and convective rain. Then you tell me, sir, what is the interface? At the interface, what will you do? First, we'll have to do a classification problem. Therefore, you come back to machine learning, you come back to data science. First, based on some parameter, there will be a threshold reflectivity. If the reflectivity is less than this and simultaneously something brightness temperature measured by this thing satellite at the same time is less than this, blah, 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 whatever, then it is reflectivity is very less and brightness temperature is more, then it is brightness temperature is less and no. If high reflectivity means the rain is very high, therefore the brightness temperature will also be low. So you have features or attributes, then you have additional proxies, and then you see that one shoe size may not fit all. Therefore, one R equal to CZ the D is not working. So that could be C1 D1 here, C2 D2 D2. I don't know. So or the radar has to be serviced. We don't know. So there may be other things. Okay. Now this is the Hofmöller diagram. So basically showing north-south shifts in precipitation across Africa. Annual average precipitation in Africa. Annual variation of precipitation in Africa, month-wise, January to December. So the latitude is basically minus 30 to plus 30 because Africa extends only from minus 30 to plus. So you can see it's very creative. So the whole of Africa is actually represented. The geographical extent is actually represented by the y-axis. The temporal or the time is represented by the x-axis starting from January to December. And there is a color coding which is given at the bottom, the average precipitation rain per rate. Therefore, as expected, in the intercontinental tropical convergence zone, plus or minus 7 degrees centigrade, you're having more rain, which is given with the blue patch. The blue patch is showing more rain, and Africa seems to be having more rain during January, February, again November, December, and during the summer, it is not having much rain. So this is what you can deduce from this. Also, you can see that there is a pattern, there is a temporal shift, there is also a geographical shift. So you can, so much of information is creatively brought out in just one simple plot. Instead of how many figures we will do, graphs you will draw. Okay. So this is a smart way. So this can be used in exploratory analysis. Okay. Now, so this is box plot. I don't know how many of you are aware. This box plot is very much used in atmospheric science and climate change, and even in engineering we use. Particularly in atmospheric science and climate sciences we use this. Box plot is a standardized way of displaying the distribution of data based on a 5-point summary. Interquartile range, IQR. So you just look at the median, and then the IQR is equally distributed, starts from Q1 to Q3. Now, whiskers are shown in blue color. Okay. Outliers are shown at green circles. Outliers are basically outside the 99.5, 99% plus. Look at the top right hand side. Look at the northeast corner of the plot. You can see that 4 green points, they are called outliers because they're outside. Now, median is basically the yellow. Okay, the Q2 or the 50th percentile. Then the first quartile is Q1. Look at the top plot. Q1, which is the 25th percentile. The third quartile is 75th percentile. The maximum is Q3 plus 1.5 IQR. Okay, Q3 plus 1.5 IQR, that means it is already covered. It is already covered. So if you do plus 1.5 IQR, rather, if you go from minus 1.5 IQR to plus 1.5 IQR, you would have covered 99.3% of the data. Anything which lies outside is an outlier. So this is the funda. This is basically statistical. This is basically distribution. Okay. Now I will say that. So this is basically from my student Baki Harish. I thank him for this. So basically, this is the Varda during the very severe cyclonistic Varda rainfall over the Chennai region. Various points around the Chennai region, Perambur, Mylapur, Mambalam, Mylapur, Mount Road, Alwarpet, whatever. So 1.9 and all this. These are all for a particular time. And now you are trying to plot this distribution. Now the orange color median shows that the average rainfall is 4.08. First quartile, okay, is that is Q1 minus median minus 1.5 IQR. 2.3 millimeters rainfall. Third quartile is 7.1. Lower whisker is 0.271. Upper whisker is this thing. And some outliers. There are some outliers in some place. For example, very close to the beach or something in the Portress or somewhere in Mandaveli or somewhere it rained too much. So all this whole data is very nicely presented in the form of a box plot. This gives you an indication of what is the average, how is the distribution, and how many outliers are there. So this is creative plotting. Please try to plot as creatively as possible in your research, in your thesis, in your papers, in your presentation. So they will know that. So this also, please don't try to look at the Google and find out what are the various ways in other people have plotted. Forget about others. What literature survey literature? We are there to create. What we do becomes literature survey for others. We have to create literature. So always don't be guided by what other people have done in the past. If you're so worried about that, you'll never do a PhD because already much has been done. Therefore, what have you done? So look at creatively plotting from a new perspective. All right. Okay. So this is a Taylor plot. This is a very, very intricate plot. Okay. So this is in polar coordinates. Taylor plot is used to quantify the degree of correspondence between the modeled and observed behavior in terms of 3 statistics. The Pearson correlation coefficient, which I'll explain in the next class. It is a cosine of the position vector of any point. Okay. Standard deviation, distance from the origin to any point. RMSE, what is a root man? It is okay, but if you're recording and putting it on the YouTube and somebody say, for you, you're attending, it's okay. They will say, look at how IIT professors are making slides. Huh? Okay. Huh? All right. So this is the general Taylor plot. Now what we have done is this is basically taken from our paper. Baki Harish, who just submitted his PhD thesis on. Baki, are you there?
Yes, sir. I'm here, sir.
You tell one. I'll give you 2 minutes. You explain your thesis.
So my thesis is all about improving the prediction of tropical cyclones over the North Indian Ocean that consist of Bay of Bengal and Arabia Sea by using weather resistant forecasting model, which is a atmospheric simulation system, which has been used by many researchers and scholars. So the main goal is to calibrate the model parameters of the WRF model and to improve the prediction of these tropical cyclones. We did this in the 4 stages. The first one is we identified best physics schemes. And then in the second stage, we identified the parameters which are influential in these best physics schemes. And the third stage is calibrating the influential parameters. And the final stage is using this calibrated model combined with assimilation and the final improvement we have observed.
Okay. That's it, Harish?
Yes, sir.
Okay. Very good. So Harish is just going to TU Delft for a postdoc. He is not even defended thesis. He's already got a postdoc. So he will apply all his fundas to look at what is that wave energy and solar energy. Is it in the Netherlands? Or tidal
Yes,
energy?
Wave
energy.
and solar energy. Sir.
Wave and solar energy in Netherlands. All right, very good. Now this is from our paper. Sandeep, myself, there's one more Balaji, Professor Balaji, S. Balaji, and Baki Harish. Okay, so this is a very intricate plot. We looked at various schemes. The right side, all those things are G.D. Morrison, this thing. People who are working in numerical weather prediction will know these are all various microphysics schemes, right? Microphysics and cumulus schemes.
Cumulus physics schemes. Yes, sir.
Cumulus physics schemes. All right. Now, they are all indicating different color. Now we are comparing the model with observations. So, what are the key quantities of interest to us? There are 2 quantities only. SLP, the CSLP, which is central sea level pressure, which is indicated as green in the text on the left-hand side. And my favorite color, orange, which is MSW, maximum sustained wind speed. So now we are looking at the error statistics. So the Taylor plot gives you error statistics. Okay, I come again. Taylor plot shows a very, very high funda way of what is that? Describing error statistics. Okay. Of what? There's a comparison between the observations and different combinations of model simulations. Okay, those engineering students, my students, if there are any other engineering students, Girish Kumar, Suraj, and all the Sayan, you should just see how we apply in engineering also, because this is a very good practice. These are done in the earth science, atmospheric science, and so on. So there is so much of stuff in this plot. Okay, it will take a half an hour for us to go through this. I'll try to explain it. And so it's very rigorous. Okay, first the variables are normalized to make it possible to show different units on the same plot. Okay, points. Now if we see outer, the sector, 0.1, 0.2, 0.3 is the correlation coefficient. Correlation coefficient gives you an indication of the closeness of the model with the observation. So if the correlation coefficient is 1, it's very good. So that is the horizontal x-axis. Okay. The y-axis in that case is 0.0 is the worst. That means there's hajar error, too much error between the model and the predictions. Okay, that is the first coordinate. The standard deviation, which is represented as 0, 0.25, 0.5, standard deviation in the standard deviation of the error, okay, in the SLP or the MSW, okay. Now you can draw various arcs. So if you look at the topmost, next to that sector where you have put the gradation, scaling 0.1, 0.2, go to the next one, where that 1, 2 are indicated. So where that 1, 2 are indicated, if you're, I put the cursor here. So now this 1.5 means there's a standard deviation of 1.5. All the points on the dash will indicate 1.5. Therefore, any point can be represented. It's a 2-dimensional plot. Therefore, to fix the state of the system or to fix the state of a particular state of affairs, 2 points are there. Now, come to this cluster of points. So 1 and 2 are the error statistics in respect of the standard deviation as well as the correlation for the 2 quantities, central sea level pressure and the maximum sustained wind speed of various cumulus models. Now you can see that 1, 2, 3, 1, 2, 3, all these colors represent various schemes. 1 and 2 represent the 2 quantities, and the Taylor statistics are indicated in this figure. Now, these 2 statistics can also be related to something called the reference point, and the reference is indicated on the x-axis. So the reference REF means 1. That means if any point is put on the reference, it is having a correlation coefficient of 1, a standard deviation of 0, and a reference value of 1, which is ideal, which is like God. Okay. So now the actual distance of any point from that reference point will tell you how good or how bad the observations are, the model simulations are with respect to the observation. Now you can see. Now class, please tell me which is the best in terms of quantity 2. Which color? Okay, let's say quantities 1 and 2. Which is having the best Taylor statistics? Pradeep? Anybody? How many people are there in the class? Okay. All right. So I'm able to see that the violet, the purple, which is NSAS, is it? Baki Harish?
Yes, sir. One guy already mentioned that NSAS and Morse scheme which has a.
So where have you mentioned NSAS?
From top to fifth, from top to fifth.
No, somebody's coming on chat.
Yes, sir.
NSAS, Aditya, very good. NSAS is the best. So this is a very involved plot. So it is very good. So think of what is that? So think of something like this. All right. Now, anomaly plot. Okay. Anomaly is basically the difference with respect to mean or with respect to some other. Anomaly is a difference. Now, it is used to show time varying extreme outliers in the observed fields relative to the mean fields. The mean can be anything such as seasonal and climatological. Okay. Mean is shown on the datum 0 line, whereas the anomalies are subtracted from the mean. So this is taken the France surface air temperature anomalies relative to 1981 to 2010 from January 79 to 2000. So basically this is Copernicus ECMWF, the European source. Okay. The first graph shows you the mean anomalies for every month for the last 40 years. Okay. Blue means that the anomaly is negative, the temperature is lower, and red means the temperature is more. So it gives you a lot of spikes, ups and down, up and down, up and down. Now, if you do a 12-month average, okay, and if you do a running 12-month average and plot it, okay, so what it means is the top plot is with reference to the global mean, okay, with reference to the global mean, you take that month's temperature and subtract it, and then find out is it higher or lower and plot it as an anomaly. If it is lower, blue color, go below the x-axis. If it is positive, red color above the x-axis, and you'll generate 12 into 40, 480 points. Then remove the points and just draw them, connect all of them through some lines or whatever. So this is the anomaly distribution. Now, if you do a running average, you can also do a running average. So this it clearly shows you now compared to the monthly anomaly. If you do the 12-month anomaly for France, it clearly shows that the last 30 years, the temperature, the anomaly is positive. It is red. Therefore, the temperatures, the surface air temperature in France seems to be continuously increasing. There have been 1 or 2 years where it is blue is there for probably 2009 or 2010, but leave it. Generally, if you look at the overall trend, you can see that the last 30-40 years, there has been an increase in the air temperatures. This is also, you can also infer it from the top plot, but it is not very clear because the blue and the red line seem to be equally spread around the x-axis. But 12-month average, decadal average, 3-yearly average. So what have you stuff? So you have to think, you have to, don't surrender yourself either to the computer or to literature or to some books or, so God has given us a wonderful tool called the brain, okay, the mind. Use this and you jugaad, whatever, you do whatever you want, and then creatively plot this and come to your own inferences. All right. Okay. Now, a brief note on statistical concepts. We have another 5 minutes. So I will start with statistical concepts. So this brings us to an end of introduction to data science. So data science itself is, so this is what is called as a foundations. What I taught is basically foundations, a large part of foundations of data science available in many universities, many online courses. So this will usually go on for about 20 or 30 lectures. So I compressed it into 3-4 lectures and made it presentable. And if you have noticed that we have worked hard to give examples from atmospheric science and climate science, and so that the interest is maintained in the class. So the foundations of data science is over. Now we have to get on to statistics, estimation, regression, machine learning, neural networks, and so on. All right, fine. Now, random variable. A random variable is a variable whose value I'm sorry, I'm highly sensitive to mistakes. Okay, okay. I'm intolerant to mistakes, my own mistake. A random variable is a variable whose value is a numerical outcome of a random phenomenon. Random variable. So you must have studied in a lot of stats courses. Random variable X, okay, which is a nightmare. X, okay, we see the X factor. Why the X factor is basically it's random. Okay, the X factor in my life. Okay. Okay, so the X factor is that X is a random variable. A random phenomenon, a phenomenon is denoted random if its individual outcomes are unpredictable, although a regular pattern of outcomes emerges in many repetitions. Toss of a coin is a random variable, but if I toss it, an unbiased coin, if I toss it 100 times, it is likely that either 50-50 or 51-49 or 49-51, I'll get heads or tails. Okay, so that is a random phenomenon. Okay, it is, we say that he is irregularly regular to the office or is regularly irregular to the office. Okay, consistently inconsistent, inconsistently consistent, consistently consistent, whatever. Okay, discrete random variable. Let X be a random variable. It is a discrete random variable if it can assume only a set of discrete numbers n equal to 1, 2, 3, 4, 5, whatever. Okay, the dice 1, 2, 3, 4, 5, 6. Only 6 value. You can't get 1.34 or 2 point whatever. So it is a discrete random variable. Heads, tail, only 2. Continuous random variable. X is called a continuous random variable if it can. Okay, we can forgive that. If it can assume all values of real numbers. Okay. Now comes the probability distribution. The assignment of probabilities to the values of random variable X gives the probability distribution f of X. Okay. F of X is a non-negative number or a function. Okay, so basically sigma f of X, okay, sigma f of X n equal to 1 to n. Now, what did you do? Okay, n equal to 1 to n equal to 1. The sum of all the f of x's will be equal to 1 if it is discrete. If it is continuous, minus infinity plus infinity f of x dx equal to 1. This is a continuous random variable. It's a discrete, this is continuous. Okay. Now, the expected value or the expectation of a random variable of X, the expectation is called E of X. See, even without realizing, when is he expected to come? Okay, what is the expected time of arrival of the flight? What is the expected time of arrival of the Amazon package, which is bothering all of us? Okay, so the expectation is E of X. Okay, so expectation in simple words, also the mean. Okay, so the mean means it will go. It could be a weighted mean also. Okay, so the EX is the weighted mean of all possible values of X multiplied by the respective weights. So sigma n equal to 1 to n. You have to do that. Okay, x of n into f of xn. Okay, so this is E of X. Now, if it is continuous. Okay. Now, those people who are threatened by the maths, don't worry too much, because it's simple to do it. The expected value of X is nothing but the weighted mean of all possible values of X multiplied by the respective weights. Okay. All right. Usually, for example, okay. quiz 1. I scored 90%. Quiz 2. I scored 70%. Final exam, I scored 80%. But now say the institute says a rule that the weightage 20, 60%. So that sigma is 100%. Now, what will be my final total? What will be my grade? Okay, that is a grade in the obsession, right? So, contribution. $18, 14, 48, 62, 70. Okay, you got 90% in quiz 1, but with that you cannot get a grade which somebody will get if somebody scores an overall of 70. So basically, this is the weight. This is the f of x. This is the x, whatever, and this is the weight. Therefore, that is your total marks, and that is how it is calculated. If f of x equal to 1 by n, ex is the arithmetic mean. Suppose there are only 2 exams. Mid-semester exam is 50%. End semester exam, final exam is 50%. You just add the 2 marks and divide by 2, or just 50-50 add, make it into 100 and release the grade. So then it is the arithmetic mean. Okay. The expected value of a function g of x is basically for random variable x, let f of x be the probability. F of x is always the probability. But now the expected value of a function g of x, instead of just saying x, there is a g of x. So therefore, e of g of x is given by a sigma n equal to 1 to n, g of x, f of sigma of g of x into f of x, and x is discrete, integral minus infinity to plus into g of x, f of x dx, when x is continuous. Okay. So I will stop here. So I don't want to do overload. So next week, we will start at, can we start at 4:15? And I will give a break.